Welcome to this explainer. Today, we're diving into a really fundamental problem in robotics, something we call the driver's dilemma. It's one thing for a clever algorithm to just draw a route on a digital map, right? But it is an entirely different, massive engineering challenge to make a physical, heavy machine actually follow that line smoothly and accurately in the real world. Let's jump right into how autonomous systems pull off the paths they plan. Here's our roadmap for today. We're going to hit 1. The motion control challenge, 2. PID control fundamentals, 3. The dual PID architecture, 4. We'll introduce model predictive control, and finally, 5. The MPC optimization framework.
Section 1, the motion control challenge. Okay, so imagine you've got a perfect, totally collision-free route plotted out from your start point to your destination. That's your path planning phase, all done. But now you have to actually drive it. How do you take that digital geometry and translate it into the physical actions of turning a steering wheel and pressing down on the gas pedal?
Well, that brings us to our core concept for today, trajectory tracking. Simply put, this is the computational process of executing that planned route. It does this by sending precise, real-time commands straight to the robot's actuators, its motors, its steering columns, the whole shebang. It is literally the bridge between a digital map and physical real-world movement. Now think about the raw path an algorithm like A-star spits out. Sure, it's strictly collision-free, but it's usually full of sharp 90-degree turns. A physical machine just can't execute those without fully stopping, turning in place, and accelerating again. To keep things moving continuously, that jagged path has to be mathematically smoothed into what we call a kinematically feasible trajectory. But here's the kicker. Even with a beautifully smooth curve, the robot still needs a hardcore strategy to actually stay on it.
Section 2. PID control fundamentals, the old reliable of motion control.
The proportional integral derivative controller, or PID for short, is by far the most widely deployed feedback control strategy in robotics today. At its core, it's entirely reactive. It continuously calculates an error value, which is basically the difference between where the robot currently is and where it's supposed to be, and then applies a correction based on proportional, integral, and derivative math. Basically, it's just constantly reacting to its own mistakes.
But there's a pretty big catch here. PID is fundamentally a SISO algorithm. That stands for single input, single output. It takes exactly one error signal in, and it spits exactly one control command out.
To really wrap your head around why that's a problem, imagine driving a car, but you can only focus on the steering wheel or the gas pedal, never ever both at the same time. I mean, no way, right? If you need to steer and accelerate to smoothly drift through a curve, a basic PID controller is gonna struggle immensely. It just isn't built for that kind of complex, real-world coordination. Section 3, the dual PID architecture. Let's look at how engineers actually hack this limitation. Let's take a standard differential drive robot, say a turtlebot, which we often model mathematically as a unicycle. Because it physically can't just slide sideways, moving it smoothly requires two totally distinct control inputs happening at once. It needs linear acceleration to manage forward speed and angular velocity to manage its steering heading. Like we just talked about, a single PID loop literally can't output both of those. So the clever workaround is a hierarchical dual PID setup. It essentially runs two completely independent SISO loops right alongside each other. First up, you have a steering PID that specifically wrangles the heading by looking at the angular error. Then you have a speed PID controlling the velocity based on the speed error. By working in tandem, they fit the complex driving behavior the robot needs, even though mathematically they aren't actually talking to each other.
Section 4. Enter model predictive control. This is a massive paradigm shift.
To quote our source material directly here, model predictive control uses an explicit plant model to predict future behavior and optimize control inputs over a finite horizon. That's a mouthful, but the takeaway is huge. Unlike PID, which is only freaking out about the error happening right this exact second, MPC is looking 10 seconds down the road. It actually uses a mathematical model of the robot's own physical limits to see into the future. And because of that foresight, MPC is a true multiple input, multiple output, or MIMO controller. It doesn't need to juggle separate, hacked-together loops for speed and steering. It solves for all those inputs simultaneously in one big optimization problem. It acts exactly like a professional race car driver, perfectly balancing the wheel and the pedals at the exact same moment they enter a curve. When you compare how they actually drive, the difference is night and day.
A reactive PID controller tends to oscillate. It gets jittery, anxiously swinging back and forth around the intended path as it overcorrects, especially coming out of turns. But MPC, it tracks the curve with incredible buttery smoothness. It doesn't overshoot because, well, it knew the curve was coming before it even got there.
Section 5. The MPC Optimization Framework. Let's pop the hood on this and see the math happening every fraction of a second. At each time step, the MPC does 3 crucial things. First, it predicts behavior over a set future horizon. Second, to make the math actually solvable in real time without frying the computer, it linearizes the robot's complex mechanical equations. And third, this is where the magic happens. It solves an objective function. This is a mathematical balancing act where the controller minimizes the trajectory tracking error, while at the exact same time minimizing the raw control effort required. It literally calculates the smoothest, most accurate path possible. And the results of that math? Absolutely staggering. When you look at the tracking error data, MPC stays incredibly tight, hovering right near zero almost the entire time. It anticipates upcoming curvature flawlessly. PID, on the other hand, shows these massive, aggressive fluctuations. It can literally peak at over 2 meters of error as it desperately tries to play catch-up with its own momentum. But, there's a trade-off. You might assume a smoother path inherently uses less energy, right? Actually, scratch that. It's the exact opposite. MPC consumes substantially more cumulative control energy than PID. That extra energy reflects MPC's aggressive, relentless pursuit of tracking accuracy. It applies sustained, deliberate forces to hold that perfect line, whereas PID allows for a bit more slop, which ultimately burns less actuator energy over the long haul. So, we finally arrive at the ultimate engineering trade-off of this whole explainer. On one side, we have PID control. It's simple to implement, reactive by nature, surprisingly robust, and relatively energy efficient. On the other side, we have MPC, mathematically complex, computationally heavy, incredibly predictive, and devastatingly accurate. Which brings us to a pretty compelling final thought. As robotic models just keep getting heavier, faster, and more complex, operating in these incredibly tight dynamic environments, which side of the scale will engineers favor? Will the future of autonomous navigation belong completely to the computational demands of predictive perfection, or will we always keep relying on the simple reactive efficiency of the old reliable PID? It is an absolutely thrilling frontier to watch. Thank you so much for joining me for this deep dive, and keep learning.